in our plasma. We depend on the presence of red cells. We deal with solutions and solvents in our bodies all the time. However, we're more concerned about the compounds in our food. Mixtures can be filtered out. Mixtures can be separated. We can take milk and separate it out into butterfat. We can separate out the water and the fat and the cream. I mean, how do you think we get skim milk? We simply filter out the fat. We can filter sugar out of iced tea. If you really wanted to make your sweet tea unsweet, you could filter out the sugar. But a mixture is only physical. There's no chemical change here. Compounds are different. Compounds are what our body depends on. Compounds involve a physical change. Compounds are held together with chemical bonds. It's a chemical relationship between the different atoms in a molecule. And these chemical bonds allow the molecule to carry energy. It has to do with the electrons. They share, atoms will share electron. Go ahead, it's okay. So just do it fast because then it's over, you know. So the calories in your what are those Doritos? So
saying about her computer backup.
Oh,
But it's not hers. It's actually really cool.
yeah, actually it is. So anyway, are those Doritos, by the way? Okay, see, now the Doritos have calories in them, and that's a good thing. The calories represent energy. When the Doritos were made, there were chemical bonds that were formed between the ingredients that store energy. You can, if you read the label in there, it tells you how many calories are in the bag.
260.
260. Okay, that's not bad. You know, the calories in there represent the total amount of energy stored in the Doritos. The energy is based on the chemical bonds, the chemical relationships that the atoms are making with each other in the carbohydrates and in any fats and anything else that are any protein or whatever else is in the Dorito. The chemical relationship they have by sharing their electrons. So because electrons spin in orbit around the nucleus of the atom. The further away they are, the more potential energy they have. So if you are not near the center of the atom, you've got a little more free energy. That free energy is what we measure in the calories. So we like calories in anything, like your Dr. Pepper or your Doritos, or double set of Doritos today. So whatever, if you're eating anything, and that's fine. It doesn't bother me. The calories are a measure of the energy contained in the chemical bonds done by the electrons, the presence of the electrons. It's stored energy in those electrons. Didn't realize that eating was so complicated, did you? So, so next time you take a sip of your Dr. Pepper, you can say, hey, I'm getting some electrons now, because that's exactly what we're doing. Just don't say it out loud. People think you're strange. I've learned to keep my mouth shut when I'm out in public. So, okay. Electrons spin around the nucleus of their atom. They're in what we call electron shells. They're the orbits of the atom, the orbits of the electrons around the nucleus of the atom. If you are an atom and you have electrons, you have these orbits. We call them orbitals. We call them energy shells. It doesn't matter. And they are in orbit around Here's the nucleus right here. And this is a shell. That's a shell, that's a shell, and that's a shell. And electrons are in orbit around here. And we can have up to 7 shells. We only care about the first 3 because most molecules that we are involved with the human body only get up to the 3rd level. So shell number 1 can hold 2 electrons. No more than 2. The second shell can hold up to 8 electrons. Third shell can hold either 8 or 18. It depends on the atom. And there's only a couple places where we go above 8 on that third shell. Just be that way. Roll it underneath the podium. Okay. Now, what do you need to remember about this? Shell number 1 can only hold 2 electrons. Shell number 2 can hold 8. Shell number 3 can hold up to 18. But usually it's only about 8. So each shell is further out from the nucleus. The further the shell is from the nucleus, the less energy it takes to keep from getting sucked into the nucleus by, the electrons they're tiny. Yes, they have 1 negative charge, which balances a positive proton. Except you got all the protons in the nucleus here, all of them sucking in with all their positive energy. All their positive charges are, it's like a magnet. It's like a great big magnet here pulling against little tiny electrons. And so you have this huge magnet and 1 little electron out there, but it's 1 negative charge trying to repel the magnet. It's hard to do. And so if you're an electron in this first shell, you spend all your energy preventing being sucked into the nucleus. That would be bad. Out here, you're a little further away, so you don't have to spend all your energy to keep from getting sucked in. In that second shell, you have a little bit of potential energy because you're further away. You don't use all your energy to fight the force, the pull of the nucleus, where the protons are. The third shell is even further away. The third shell uses even less energy to fight off the force of the nucleus and has even more potential energy. And that's the potential energy that we're finding embedded in our food and in the things we drink, like the Doritos or the Dr. Peppers, or, anything we've gotten at, for coffee this morning, or whatever's, in the lattes or anything that has calories in there. The calories are a measure of the energy stored in all the chemical bonds with all the electrons that have that potential energy that's still circulating around their atoms, even while we're eating it. The electrons are still present, and it's that potential energy that they have. So they, if they're close to the nucleus, they're fighting off the pull. Further away, there's more potential energy. That's how we measure calories in food. It's a measure of the energy that's available to us all the time. So whether we're dealing with something solid food or liquid food, if there's calories in it, it's a measure of this potential energy. Okay, so this is what an atom looks like, more or less. Doesn't go that slow. The illustration is aluminum. Aluminum is an element, so it has an atomic number of 13. That means that there are 13 protons and 13 electrons. You'll notice that it has 2 electrons in its first shell. It has 8 electrons in its second shell, and it has 3 electrons in its third shell. Because 2 and 8 and 3 make 13. So that's how many electrons that are present in any atom of aluminum. because there's 13 protons and 13 electrons. The electrons that have the greatest amount of potential energy are in the outer shell, the outermost shell. We call that the valence shell. The valence electrons have the greatest amount of potential energy. So the calories that you find in your food are coming from the potential energy of the electrons in the valence shells of all the molecules in your food, the carbohydrates and the fats that are in most of your food, or the proteins too. So that's where the valence, that's where the potential energy, the calorie count in our food is coming from, the valence electrons. And they're all going to spin, all the electrons are going to spin in orbit around the nucleus. The nucleus will have the protons and the neutrons. Neutrons don't have a charge. They're not going to affect the electrons. It is simply the presence of the protons that are going to trying to pull in the electrons. The further away you are, there's less pull, and there's more potential energy. You know, to give you a perspective on the actual amount of space that we're dealing with here, if that was an atom, well, you know, if the atom was actually that big, and there's the nucleus, the first shell, the first orbital might be out to where ETSU's building is down the street. It might be that far away. The second orbital might be down to the Parkway. And the third orbital might reach Seymour. Yeah. If we're looking at, you know, if we were comparing it to, you know, something that big, the distances would be huge. So it isn't like they're jammed in there real close together. You know, if you're in, you know, these electrons are very far apart. So, but because we're dealing with something that is, you know, the size of an atom, as far as the atom's concerned, it's immense distances. Anyway, the valence electrons have the greatest potential energy. Now, atoms are picky. They like to fill up their valence shell. They want to be stable. An electron wants to have its valence shell full. Hydrogen wants to have, you know, hydrogen has one shell. It has one electron. It wants to have a second electron in there. It wants to be full. It wants to have 2 electrons in its first shell. It doesn't. Hydrogen only has 1 electron. Helium has 2. Helium is very stable. Helium is inert. Helium reacts with nothing. Helium is, you know, pretty boring actually. But hydrogen, on the other hand, because it really, really wants to fill up its valence shell, even though its valence shell only holds 2 electrons, it really wants to get a second electron in there, and that makes hydrogen very reactive. Hydrogen reacts with everything. So now hydrogen and helium are the only ones that have 1 and 2 electrons. You know, hydrogen has 1 electron, helium has 2. Everything else has a second shell and can hold up to 8 in its second shell. Everything that has a second shell wants to fill up that shell. You know, for example, carbon has an atomic number of 6, 2 electrons in its first shell and 4 in its second shell, and it really wants to get 4 more electrons in there. So carbon is very reactive. Carbon combines with anything, usually hydrogen. Because atoms like to be stable. They don't like to be out by themselves as an atom. They like to combine with other atoms so they can fill up their valence shells. Atmospheric oxygen has an atomic number, elemental oxygen has an atomic number of 8. 2 electrons in its first shell, 6 in its second shell. We don't usually see elemental oxygen. What we're breathing is what's known as atmospheric oxygen, or O2. Oxygen combines with another atom of oxygen, so it will be able to share their electrons and become stable in that second shell. Because all they want to do, all an atom wants to do is be stable by filling up its valence shell. Now, the atoms that are chemically non-reactive are the ones that have their outer shell, their valence shell filled up. Helium is not reactive. Helium reacts with nothing. It won't burn. It won't combine with any other compound. It is stable. Bless you. The same with neon. Neon has 10 electrons, 2 in its first shell, 8 in its second shell. Neon doesn't combine with anything either. Neon is inert. It's what we call these are what we call the noble gases: helium, neon, argon, and krypton and xenon. These are all chemically inert. They're stable. They don't do anything. We use neon for lighting. We use argon for fire suppression because it doesn't, and xenon for fire suppression. We use krypton for insulation in windows between the layers of glasses because they don't react with anything. They just take up space and, are there. Very few atoms are like this. Most atoms, however, are reactive. Reactive atoms are trying to get electrons. Hydrogen only has 1 electron. It wants to get a second one. Carbon has 4 electrons in its outer shell and wants to get 4 more. Oxygen wants to get 2 more. Sodium has 11 electrons. It has 1 in its valence shell, and it would like to either get rid of that electron or gain 7 more. Because even though it is balanced, 11 protons and 11 electrons, it's not stable. It wants to do something, so it has a balanced number of electrons as far as it's concerned. So these are all reactive elements. Anything that has an uneven number, anything that doesn't have a full number of electrons in its valence shell is going to be reactive. And again, the reason that we care is because we look at the energy that is associated when we have 2 reactive atoms and they come together. We've got energy in, stored in those atoms. So chemical bonds, we're dealing with chemical bonds. Chemical bonds contain stored energy. There can be a lot of energy stored, there can be a little energy stored. 3 types of chemical bonds. We have ionic bonds, we have covalent bonds, and we have hydrogen bonds. Ionic bonds are very simple. Ionic bonds are simply between, usually in salts, like sodium and chlorine. In fact, table salt, sodium chloride, is the most common type of ionic bond we deal with. For an ionic bond, we have to create ions. Now, a regular atom is neutral. Sodium, for example, 11 protons, the atomic number for sodium is 11. It tells you it has 11 protons and 11 electrons. 2 in the first shell, 8 in the second shell, 1 in the third shell. It's balanced. But an ion is an atom that has lost an electron or gained an electron. So to become an ion, you have to acquire a positive or negative charge by either gaining an electron and you become negative because now you have more electrons than you do protons, or you lose an electron, so you have more protons than you do electrons. Turns out that most of our ionic compounds we deal with in our bodies are salts: sodium chloride, potassium chloride, calcium carbonate, calcium chloride, magnesium chloride. These are all going to be salts. We are so used to dealing with sodium chloride, table salt. We might see potassium chloride in a salt alternative, for example, like you ever hear of dashes? It's a salt substitute, because later on we'll talk about why we don't like to give people with hypertension extra salt. So anyway, the ionic compounds in our bodies show up as salts, and sodium chloride is the #1 ionic compound. Salts form crystals. If you were to look at sodium chloride under the microscope, you would see it is formed in crystals. And if we could look at it with a sufficiently powerful microscope, we would see it looks like the animation there, consisting of sodium atoms and chlorine atoms held together in a framework. They are attracted to each other because of what we call these ionic bonds. So how does an ionic bond form? Well, ionic bonds occur when one atom gives up an electron and the other atom grabs that electron. So for example, sodium doesn't like its 11th electron. The 11th electron is way out there in its valence shell. The valence shell is out by Seymour, and its little electron floating around by itself. And sodium says, goodbye, I don't like you, get out of here. Sodium gives up the electron. Sodium now becomes positive. Because, why positive? Because it still has 11 protons and only 10 electrons. Instead of being neutral, balanced with positive and negative charges, positive protons, negative electrons, it is now positive because it has more protons than it does electrons. So an atom that gives up an electron is called a cation. It's positive. It's like the positive end on your battery, your car battery, for example. That is the cathode end, or the positive end on a regular little battery you put into your flashlight or something. The positive end, because that is the cation side or the cathode end. This is, if you're an atom, you are a cation. You're positive. If you gain the electron, we don't like electrons to be running loose. We generally require the atoms to stay balanced one way or another. So if one atom gives up an electron, another atom has to grab that electron. In this case, it's chlorine. Chlorine grabs that random electron that sodium gave up. And now chlorine is also an ion. It is negatively charged. Because chlorine has an atomic number of 17, it has 7 electrons in its valence shell, and now it has 8. Chlorine becomes stable because it gained an electron. Sodium became stable because it gave up an electron. A sodium ion has 11 protons and 10 electrons, 2 in its first shell, 8 in its second shell. Chlorine is now a negative ion. A fluorine ion. It has 2 in its first shell. It has 8 in its second shell and 8 in its third shell. It's no longer an atom, it's an ion because it's not balanced. It has more, an anion has more electrons than it does protons. So what will happen is that these positively charged cations that have given up an electron and these negatively charged anions that have gained the electron are going to be attracted to each other like magnets. We call it electrostatic attraction. That's an ionic bond. It's sort of like being held together by magnets. It is an electrostatic charge on here. It holds them together. Sort of like using anybody ever use a Swiffer? You know what Swiffers are, right? Okay. You put that little cloth in the bottom and you push it like 3 times and it's filled up with dirt and you have to get another one. Great marketing scheme. It's like buy lots of Swiffer cloths. I mean, it works. It works. It works because moving the Swiffer cloth across the floor creates a charge on the cloth that attracts the opposite charge dirt and dust particles. The reason that dust and dirt jumps onto the Swiffer cloth is that you know, by the friction of rubbing that cloth across the floor puts a charge on the Swiffer cloth that's the opposite charge. It's on the dust and dirt, and it sucks it together electrostatically. That's what it does. And it's not a very strong attraction, but you know, it works. Now in ions, they have an electrostatic attraction because the positive ion is attracted to the negative ion, and it comes together to form a crystal. Sodium, you know, this is what sodium does. Sodium gives up its 11th electron and it gives it to chlorine. Chlorine grabs it. So now sodium's valence shell only has 8 electrons instead of 1. And sodium has 10 electrons total instead of 11. Chlorine has 18 electrons instead of 17. Chlorine's negative, sodium's positive, and they will array themselves always in this crystal type structure of, you know, sodium, chlorine, sodium, chlorine, sodium, chlorine, held together electrostatically. It's a very weak chemical bond. It breaks very easily. If you've ever put salt into water, you break the bond very easily. Now this is salt water, and maybe some other things growing in there right now. But salt water, you mix salt and water together, and what happens to the salt crystals in water?
They break down.
They break down, exactly. They disappear because water breaks apart the electrostatic bonds, the ionic bonds, holding the sodium and the chlorine together. Take away the water and they come back. That's what's happening there. We're losing some of the water and the salt crystals are starting to form up again. So it's a very, very weak chemical bond. It easily breaks apart. And so we see these salts generally will form as crystals if we give them enough time. You know, and that's something that affects our bodies. Consider kidney stones. Kidney stones occur when we have excess ions in our kidneys, usually calcium, you know, some form of calcium. And calcium, like maybe calcium chloride or calcium carbonate or something like that. And the calcium starts, these, which is normally in solution in our plasma, starts to form crystals in our kidneys. And these crystals grow. And if anybody's ever had a kidney stone, it's described as an excruciatingly painful experience in trying to, when the stone forms and then pass down through the ureter into the bladder and out through the urethra, because some of these stones can get very large and they have razor sharp crystals on them. And people describe it as unbearable or excruciating pain. So crystals are important to us in this case. You know, if we allow these salts to start forming crystals in our bodies, you know, the bile that's in our gallbladder, if there's more bile than we need, sometimes that bile starts to crystallize and form salts in there. We call them gallstones, which can block the bile duct that lets the bile go into the small intestine. It also causes the gallbladder to become infected and you know, all sorts of, you know, it leads to a lot of people having their gallbladder taken out. So anyway, so most of our crystals, though, most of our salts stay where they belong in solution. That's nice. That's what they're supposed to do. They're not supposed to be crystallizing in our body. If they're crystallizing, something's going wrong. Now, ionic bonding, though, is not a very strong bond. It breaks easily. In our case, we like that because we like to have our salts, and we need lots of salts. We need sodium and chlorine. We need potassium in our bodies. Our muscles depend on the presence of sodium on the outside of our muscle cells and potassium on the inside. It's how we generate the nerve impulse to cause our muscles to contract. Our nerves depend on sodium and potassium ions so that they can send a nerve impulse down across nerves. So sodium and potassium ions are very, very important to us in solution, not as a crystal, but as an ion. So we like the fact that these ions form but are held together with very, very weak bonds. We need the sodiums, we need the potassiums, we need the calciums, we need the magnesiums, we need stuff like this in solution. So we like the fact that the bonds are very, very weak. Ionic bonds don't hold together at all. They break easily, they form, they break, they form again. So now the second type of chemical bond is what's known as the covalent bond. Covalent bonds occur when we share the electrons. Instead of stealing electrons or kicking out electrons, a covalent bond is when we share electrons from the valence shells, where we can share between 2 atoms or 3 atoms or 4 atoms. When we share 2 electrons or 4 electrons or 6 electrons, most of the sharing we have takes place with 2 electrons. We call it a single bond. In some places we have a double bond where we're sharing 4 electrons, and occasionally we'll have a triple bond where we share 6 electrons. But most of the electron sharing we have in a covalent bond is going to be 2 electrons. What covalent bonding does allows the valence shell to be filled up because they're sharing the electrons. They're sharing, 2 atoms can come together and share electrons so that at least part of the time, each atom will have its valence shell filled up. Consider hydrogen. Hydrogen has 1 electron in its valence shell. If 2 hydrogens come together, each one's bringing an electron along. If they combine and form a molecule known as H2, or atmospheric hydrogen, the hydrogen atom on the left is sharing both electrons. At the same time, the one on the right is sharing both electrons. How can it do that? Well, remember, these electrons are moving at 186,000 miles per second. They're moving so rapidly that they're here, they're there, they're here, they're there. And so essentially, the valence shells are filled in both atoms. Because we can't discern the time difference, it takes to go from one side to the other, because 186,000 miles per second, and you're talking about atoms. It's very rapidly. What happens is that essentially the valence shell is filled at least part of the time. And part of the time is probably most of the time. So if our 2 atoms are held together by a covalent bond, then they are sharing electrons. Okay. This is a covalent bond. This is the one on the top is hydrogen. And you can see hydrogen comes together. Each hydrogen atom provides 1 electron because it only has 1 proton. But hydrogen dearly wants to have its valence shells filled up. And so these 2 hydrogen atoms bond together and they are sharing electrons. Notice how the electrons go back and forth from atom to atom, and they create a very stable compound. Atmospheric hydrogen is very stable. It's not reactive. Elemental hydrogen is reactive. Elemental hydrogen is what we saw that is lighter than air. It was used for balloons and airships back in the 1930s. I'm sure you've seen pictures or video in a history class of the Hindenburg blowing up in New Jersey back in the 1930s. It was a giant blimp that was filled with hydrogen instead of helium. Hydrogen was, it was elemental hydrogen, very, very reactive with atmospheric air, trying to find more electrons to satisfy that hydrogen. Atmospheric hydrogen didn't work. It wasn't light enough. So they used elemental hydrogen. Bad choice. Because the elemental hydrogen is reactive. Atmospheric hydrogen is not reactive. And because it's stable, it has 2 electrons in its valence shell. It won't combine with anything else. Consider oxygen and hydrogen. Oxygen readily combines with hydrogen. Oxygen has 6 electrons in its valence shell. It would like to get to 8. Hydrogen has 1. It would like to get to 2. Hydrogen and oxygen easily combine so that hydrogen can share its electron with the oxygen, and oxygen can share its electrons with the hydrogen. This happens all the time. So valence electrons are going to be shared. Valence electrons are the ones with all the potential energy too. So now how do we know that there's lots of energy available here? Well, consider this. This is an atom. Look at this atom of carbon. Carbon has 2 electrons in its first shell, 4 in its second shell. It wants 4 more. Well, carbon readily combines with hydrogen. This is also, so if carbon combines with 4 hydrogens, you get something known as methane. Methane is natural gas. What do we do with natural gas? Anybody have gas heat at home? Or a gas stove? Okay, you do. Is it methane or propane? Okay. Is there a big tank in your backyard or not? There's a big tank. Okay, if you have a big tank, then it's propane. Propane is also a gas, even more efficient than natural gas. Propane's good. Methane's good. If you have gas coming into your house, you have natural gas, which is methane. Why is that a good thing? Because the amount of energy stored in the methane from the 4 hydrogens and the carbon, it has a great deal of potential energy. So we can use natural gas to heat our houses, to cook with, to heat our water, to power our vehicles. The utility, the gas company has natural gas powered trucks all over the area. There's some of the trolleys, I think, are natural gas powered, or maybe the Dollywood, the Dreammore trolleys are natural gas powered. But you can use it to power vehicles. You can use it for all sorts of things. There's lots of potential energy in there. Now, propane is a little different. Methane molecule looks like this. Here's 1 carbon and 4 hydrogens. It has lots of potential energy, but propane has 3 carbons and it has more hydrogens. So methane has 4 hydrogens, so it's called CH4, which is methane. Propane has C3H8, and this is propane. Anybody have a propane grill? Use gas for propane grills? Yeah, okay. You go down to, Home Depot, or you go to Walmart and you get a tank of propane and you cook with it until it's empty, and you get another one. We've all done that at some point. Propane is more efficient. If you've got a big tank in your backyard and you're using propane, that's a more efficient gas than methane. How do I know? Because there's more energy there. How do I know there's more energy? Because there's more carbons and more hydrogens. Each one of these atoms bring more valence electrons, and the valence electrons all have potential energy. Nothing wrong with propane, nothing wrong with methane. Both are good sources of energy. We use them all the time. We know that there's energy there because there's more covalent bonds. The more covalent bonds we have, the more energy we have available to us to do something. So it is the sharing of the electrons between the carbons and the hydrogens, between the carbons and the carbons, that give us all this potential energy. The calories in our food are based on the valence of electrons in the large molecules sharing their sharing the electrons, sharing their potential energy. Glucose has a formula of C6H12. This is glucose. Simple sugar. C6H12O6. 6 carbons, 12 hydrogens, and 6 oxygens. A lot of electron sharing going on here to make a stable glucose molecule. And that represents a lot of energy, a lot of potential energy. So the carbohydrates that we eat contain a great deal of potential energy. Most of the calories that we find in our food often come from the carbohydrates. The carbohydrates are, we call them, they're called carbohydrates because they're the carbons and hydrogens linked together. That's why they're called carbohydrates. So how much energy do we have? Well, on a carbohydrate, we get 4 calories of energy per gram of carbohydrate. So it's not bad. Fats are better. Fats give us 10 calories per gram, but we can measure the amount of energy stored in those valence electrons. And why do molecules occur like this? Because they're stable. Methane is stable. Methane is not reactive. It has all of its valence electron shells filled up. Propane's not reactive. It's only when we ignite it. It's only when we ignite the methane that we start releasing the energy. It's only when we start breaking down the carbohydrates and the fats and the proteins that we've eaten that we release the energy in our food. A couple of points here about valence electrons. We'll call it a day. Carbon dioxide is sort of the ringer here. Carbon dioxide has an unusual shape. Carbon dioxide is in a straight line. It's a valence electron. It has valence electrons sharing their electrons, but it's carbon with 2 oxygens attached to it, 1 on each end. It is balanced. It's not reactive with anything. It is what we call non-polar. It has the same level of electrons on one end of the atom as it does on the other end. So if they were a polar molecule, they would tend to have a slight positive or negative charge. Okay. Why do we care? Well, water is non-polar. Water is polar. Water doesn't share its electrons equally. And so we see that water tends to have a slight positive end to it and a slight negative end to it. And this is a great place to stop, by the way. So, okay, questions on anything? Lab this afternoon and lab this week, we are finally going to do the cheek swabs. We are going to wrap up cells and mitosis. And if we have enough time, I'm going to start us looking at the bones of the skull, if we have enough time. So, okay. I will.